what I would say is like the conceptual, straightforward way. We're going to look at it that way, but then I also want to take a look at how the formula that we found, or I guess we didn't find, but that you guys hopefully learned yesterday, how we would use that in order to get the exact same result. And then there's a piece of that formula that's actually kind of interesting to look at from just like a what this number is telling us kind of perspective. So we'll kind of examine that as well. All right. So this is looking at a compounded event here. In this case, we have the probability of getting a positive test and the probability of actually being positive. All right. So just a quick review. On Thursday and then Friday, we looked at or statements. So this is like the probability of A or B. What did we find with or statements? What was kind of our way to deal with this setup for probability? Very good. So probability of A plus probability of B, but then we have overcounted certain individuals. The ones that we have overcounted are the ones that get shared between the two. So minus the probability of A and B. What happens if we are dealing with mutually exclusive events? What does it mean for two events to be mutually exclusive? So that's kind of getting, yeah, actually, I think that that's a good way to think about it. So events that can't happen at the same time, if they can't happen at the same time, then what does that mean about the overlap between the two? There can't be overlap, exactly. So there is no overlap, or I guess being mutually exclusive. Gave us that this was equal to 0, right? Gave us that the probability of the overlap should just be 0, no chance of them sharing. And then the formula from yesterday, this was the probability of A and B. What was this? What do I do when I'm looking at taking the intersection between two probabilities? So for instance, if I want to know the probability of getting a heads followed by rolling a 6, what do I do with each of those individual probabilities? So we could do a similar thing where we construct like the whole sample space and then go through that process, count the number of outcomes that give us successes. Certainly could do that. This is going to be computationally, hopefully a little bit easier than that, although we'll see maybe not necessarily all that much easier. So what do we find in the 4.3? What do I do to combine probabilities for my AND statements? Multiply them. Now, was it just as simple as the probability of A times the probability of B? Was it just the probability of B here that I was multiplying? And just like with the whole, like we have to subtract the overlap thing, the answer here was no, right? It's not as clear cut as just taking the two probabilities and multiplying them together. It's the idea of what is going on with the probability of B after the fact that A has occurred. B given A, yes, exactly. Right, written in this way, right? This is the probability of B given that A happened. Okay. If the probability of B was unaffected by A happening. So for instance, if I am rolling 2 die, we wouldn't expect getting a 1 on the first roll to affect getting a 3 on the second roll. What do I call those events? So if the probability of B is unaffected by the probability of A, then these events are so mutually exclusive is one thing, but that's only for or statements. Independent is what we have for and statements. So these two can get pretty easily confused, which is why I want to highlight this. If the probability of B given A is just the same as if A had never happened, then these are independent. Just says that they are independent. Right? A and B are independent. Then A and B are independent. Yes. If this, then this. Okay, so taking a look at the two events that we are considering, we want to consider the probability of both getting a positive test and also the probability of, being positive. So fulfilling both of those conditions at the same time. Are these events going to be independent? So in other words, does getting a positive test change the likelihood of a particular condition? What do we think? For instance, if you get told, hey, you have, I don't know, the flu, if a test tells you that, hey, you have the flu, does that change how likely it is that you have the flu? Maybe not like in reality, right? In reality, you either do or you don't. But as far as like as a percentage, yeah, it makes you more likely to have the flu, right? If you get a positive test saying, hey, this is your condition, then you're probably more likely to have that condition. If you get a negative test saying, hey, you don't have this condition, then you should hopefully be less likely to have that condition. Otherwise, what was the point of taking the test? Right? Why would I get test results if the test result doesn't tell me something about what is the actual likelihood that we are seeing this? So these are not independent. If they were independent, we could just multiply the probabilities together. That would not be too difficult, but they are dependent, and so we cannot just do that. Okay. So if we wanted to break this down formulaically, this is going to be the probability that we get a positive test times the probability that we get that we actually are positive, given the fact that we got a positive test. Right? That's just the formula, right? A and B is the probability of A times the probability of B given A. Okay. So what's the likelihood that we got a positive test? How many people are going to get a positive test? So say again. So 10 people. So where are we getting that 10 from? Yeah. Is that the number of positive tests that I have? No, that is the number of positive cases that I have. That's the number of positive patients I have. Okay. So 10 are positive. Of these 10 that are positive, how many would we expect to test positive? 90% of them, which would be 9 test positive. And then 1 flies under the radar. Okay. I think a lot of people just saw that 9 and then they said, hey, we're done. because that's true, right? These are the 9 people who fulfill both conditions. These are the people who are both positive and also who are testing positive. 9 out of the 1,000 is ultimately the correct answer. But let's continue going. Let's try and see if we can't fill in this this formula as we go. What if we don't know that that's where we stop, and so on. So we get 9 positive test results from the 10 that are actually positive. And then what about the 990 that are negative? How many of these will also give us positive test results? These are the people who do not have breast cancer. But how many of these people are going to be told, in fact, you do have breast cancer? 10% of them. So that would be like 99 test positive. Right, so these are like the 9 who test correctly. And these are just the unlucky ones who, in fact, do not have breast cancer, but then their screening gets back and it says, oh, hey, by the way, you have breast cancer. All right. And so what is the likelihood of testing positive? How many total positive tests? Well, that was total positive people was 10, but the total number of positive tests is going to be 108 out of 1,000. So about 10% of the people are going to test positive. A little bit more. Okay. Do we feel good with where this came from? The number of positive tests, some of which are true positives, right? 9 of them are true positives, people who have the condition, who have been caught with having the condition. And then 99 of them are false positives, people who do not have the condition, who are being told, in fact, you do have the condition. Okay? So now we need to figure out the likelihood of being positive given the fact that we have a positive test. So how many people is this talking about? If we are assuming that the people that we are describing have been given a positive test, what is our new sample size? How many people is that describing? Yeah, exactly. This is some number out of 108. And in fact, what number is it out of 108? How many of the 108 are actually positive? 9 of the 108 who were told that they have breast cancer actually have breast cancer. Okay, so what is the probability? Well, taking these two and multiplying them together, 9 times 108 times 108 over 1,000. You can switch the order around. That's really what the formula would have you do, is reverse the order, but multiplication can happen in any order we like because of commutativity. Sure. What's going to happen with my 108s? They cancel, and so we see that we have a 9 in 1,000, which is that number that we saw before, right? 9 in 1,000 people who are actually positive, who tested positive. Okay, so not a particularly surprising answer, since we had to like find this answer in order to like, you know, mathematically compute the answer, right? We kind of already knew that it was going to be 9. What I think is really, really quite fascinating here is that of the 108 people, this is from actual data done with mammograms. Of the 108 people from this 1,000-person sample, about 1 in 11 of them actually had breast cancer. So we have this incredibly accurate test, right? It gets the answer right 90% of the time. But if you are told that you in fact have a positive test result, then the chances of you actually having that positive test result are about 1 in 11. And that's just due to the sheer number of false negatives due to the sheer number of people who are negative versus the people who are actually positive. So a little bit of a weird kind of confounding thing. We have this incredibly, incredibly accurate test, but because the condition is rare enough, you're a lot more likely to be a false positive, even though this test is super accurate, than you are to be a true positive, which is just kind of fascinating. And then the other fun thing is that doctors don't know statistics necessarily super well. And so they see this positive test result and they don't know to tell you, oh, hey, by the way, that means you have about a 1 in 10 chance of actually having breast cancer. Have fun with it. They fall on the interpretation of, oh, it's closer to 90% because this test is right 90% of the time. But again, that 90% is a little bit misleading. Yeah. Where? I just thought was kind of a cool result and a very kind of surprising one. But I also wanted to highlight the way that we do the conditional probabilities here. All right, questions with our bell work here? How are you feeling with the 4-3 stuff, mostly? We'll have a lot more time throughout today to practice some of the conditional setups, but just as like a general overview. All right. So good news. Today's lesson is almost entirely going to be just review. I've already been using the notation that this is setting out to try and teach us. I have been told not to go too crazy with the word set theory. So I am not going to be going too crazy with the word set theory. We're not going to talk about really, the objects that we are actually working with, which is a little bit of a shame. But we'll keep it somewhat digestible for a high school class. Cool. So set theory. This is the notation that we have been using up until this point. When we were talking about unions and when we were talking about intersections and when we were talking about complements, these are not the unions of probability. They are not the unions of or intersections of probability. They are not the complements of probability. You could talk a little bit more about complements of probability, but even then, what we are talking about are the sets themselves. All right? The actual bubbles, the conditions, the events that we are trying to meet. And we've already seen a lot of these. So for instance, if I want to talk about the probability of A or B occurring, how do I do this? It's one of those two. So which one's or? Yeah, very good. This is going to be our union symbol, right? Probability of A or B is going to be the probability of A union B. Right, but these are talking about the sets, right? A is the set of outcomes that fulfill a certain condition. And we're combining that. We say we want at least one of these with the set that is whatever fulfilling condition B, all of the outcomes that fulfill that second condition. Sure. What is our and statement? Yeah, the other one, the intersection. Probability of the intersection between A and B. Sure. Literally where our sets kind of intersect, the shared outcomes between the two sets. And then we also have the complement. How do I say the probability of like not getting A? So that's how we calculate it, but how do we write it? What's the notation here? Yeah, we could do that. So the way that I've been showing you is A with the little C up at the top to say complement. You could also see this as A. I think the way Pearson does it is A with a little line over the top. And then the way we're going to see it today is A with a little apostrophe. And all of these mean the same thing. It's just not A, right? Everything that is not inside of A. And we've already talked about these. What is our addition rule? What do we do when we want to find the probability of A or B? Minus the intersection. Yeah. Okay. And then what is our probability for multiplication for A and B? Well, we just spent a whole bell work on. Very good. Probability of A times the Bayesian probability of B, given the fact that A has happened. Yes, there is a formula for probability of B given A. It's a little bit tautological. This ends up being like the probability of A and B divided by the probability of A. Which is literally just dividing the probability of A on the equation that we have on both sides. So again, it doesn't really tell us new information. It's just a way of rehashing the same information that we already have. But there you go. If you needed to just find the conditional probability, that's how you can do it. Sure, we have a formula for it. Why not? I am going to be focusing on conditional probability in a much more conceptual way. So just thinking about like, okay, if A has happened, what is our sample space? What is our sample size? And then how many of those fit the condition of B that we're trying to fit to. Cool. All right. So in this case, we are trying to figure out the sets or the outcomes that satisfy the conditions that we are trying to get. All right. So notice here what we are not looking for. We are not looking for a probability. Right. We want here all of the outcomes that fit this particular bill. So for instance, looking at number one, if I'm trying to figure out the intersection between set A and set B, what is shared between those sets? The number 6 is shared between those sets. Therefore, the intersection is just the number 6. Which is also a set. It's just a set that contains a single element. It's just 6. Okay. If I want for number 2 to figure out the outcomes that are either in A or in B, so A union B, what are these outcomes going to be? Um, So 6 is still going to be, 6 is in either A or B. So we're just trying to figure out what is either in one or the other. So for instance, do we see the element 1 in A or B? No. Okay, so 1's not going to be in this set. Do we see the element 2 in A or B? Yeah, it's in A. Does it matter that it's not in B to fit the bill? Do I have to go to both the bank and the store to have gone to either the bank or the store? No, I just have to have gone to 1. In this case, 2 went to the store. That's okay. We still want to include 2 in our list. Yeah, 3 went to the bank, 4 went to the store, 6 went to both, 8 went to the store, 9 went to the bank. Yep. Okay. If I don't live in A, so the complement of A, which written here, A prime, if I don't live in A, what are elements that are part of my larger set that I do not see in A? Very good. Noticing here, importantly, does not living in A necessarily mean that I live in B? No, right? We're just saying things that aren't included in A, we take all of the things and we look at the ones that aren't in A. Cool. A lot more straightforward than that. All right, take a moment to fill out 4 through 7. And then we'll look at 8 together. But we'll just take like 2 minutes here. Fill out the elements that are going to live in what we see for 4 through 7. 4, 5, 6, 7. And then 8's not hard. We just haven't seen it yet. So we'll talk about it here momentarily. All right, let's take a look at what we've got here. What are the elements that don't live in B? So everything that isn't 3, 6, or 9. Very, very good. What are the elements that are shared between not living in A, so this set here, and also not living in B, so this set here? What is the overlap between those two sets? Very good. 1, 5, 7, and 10 don't live in either. All right. Of all of our elements here, which elements at least aren't in A or aren't in B? Yeah, it's everything but 6. right? If we're trying to think about satisfying the condition, either we don't live in A or we don't live in B, the only elements that don't fit that bill are the ones that live in both A and B. And there's only one element that fits that description. That's 6. 6 is the only element. Very good, Dylan. So this would be 1, 2, 3, 4, 5, 7, 8, 9, and 10. Think about if we go this way, 1 doesn't live in either. So obviously 1 fits this description. 2 does live in A, but doesn't live in B. So it fits that description. 3 doesn't live in A, even though it lives in B. So it fits that description. 4 lives in A, but doesn't live in B. So that's fine. 5 doesn't live in either. So that's great. 6 is the only one that lives in both A and B. So 6 is the only one that's excluded. All right. For A union B, what are the elements that we are missing from this set here? What are we missing? Seven and 10. So like the exact same thing that we saw for that set here, which if you parse through the logic should make sense. All right, and then A minus B, this is actually fairly straightforward. We want to look at the things that live in A that do not live in B. All right, so we want to essentially take away any elements that they share. So what are the elements that only live in A and do not live in B? 2, 4, and 8, right? We just want to remove 6. What would B minus A look like? Just in B, which would be 3 and 9. Very good. Very, very nice. All right, questions with our set example here? How are you feeling? You'll notice it can be helpful as these get more complicated. So like if we're working at like the union between the things that live in A and the things that don't live in B, it can get tricky to kind of keep track of all of those. But if you write out what each set is that you're actually looking at, like if you write out these are the elements that don't live in B and this is just what I'm using, it becomes a lot easier. So that would be my advice. It's very helpful dealing with like 5 and 6 if we have first done 3 and 4. Otherwise, it becomes a logistical nightmare trying to keep track of everything, right? It becomes a lot easier to do 7 once we've already done 2. Otherwise, it becomes a logistical nightmare to try and keep track of everything. No questions? Easy peasy. Rather than difficult. All right, cool. Let's take a look at a couple of numerical examples. This is actually going to be kind of marrying the two, although again, we've been doing this for a very, very long time. In this case, we are looking at 2 different kind of variables here. One is the age, so we have freshmen, sophomores, and juniors, which we'll denote as F, S, and J. So that's like one potential event. And then we have their favorite toppings, A, O, M, and H. And we're being asked to figure out various things. We are going to first do the symbols and then actually do the calculations. So for instance, figuring out the probability of liking mushrooms. Actually, getting ahead of myself here, let's actually fill out the totals that we see here. So for instance, how many freshmen do we have overall? 23. How many sophomores do we have? and then how many juniors? 18, for a total of 60. Okay. How many total people really liked anchovies? 11 people liked anchovies. How many people liked onions? 17. How many liked mushrooms? And then how many liked hamburger? 20. Very good. Which should also total up to be 60. Okay, so we're trying to first write in terms of our set notation and then actually calculate the probability of liking mushrooms or being a junior. So how would I write in my set notation the probability of liking mushrooms or being a junior? And mushrooms? Yeah, this is going to be the union of, now the way Liz did this was J and M. If I switch the order and do mushrooms or juniors, would we expect that to change anything? No, order shouldn't matter here, right? We wouldn't expect that to affect anything, so this is absolutely perfectly fine. What do I have to remember when I'm doing or statements? Subtract the overlap, so we add them together, but we subtract the overlap. So what's the probability of being a junior? That's 18 out of 60. What is the probability of liking mushrooms? 12 out of 60. And then how many people did we just accidentally count twice? 5 out of that 60. So we have to subtract away an instance of 5 out of 60 to get that there are 25 of the 60 people who fit at least one of these conditions. Okay. So looking at number 2, the probability of not being a freshman, given that the individual likes anchovies. So let's first worry about how we are going to write this. So how would I indicate that we want to figure out the probability of not being a freshman? Yeah, that totally works. So F with the apostrophe. You could also do F and then little c. You could also do F and then the little bar over top. However you want to do that is totally fine. How do I indicate that I have a given condition, that we are essentially restricting our sample space here? Yeah, we do the little vertical line. So given the fact that we do like anchovies. Okay. So the only people that we are going to be pulling from are ones that satisfy that second condition. Of all of the people here, how many of them satisfy the assumption that this person is going to like anchovies? That 11 of them are going to fit that bill. And of those 11 people, how many of them are freshmen? 7 of the 11 are freshmen. Am I looking for the number that are freshmen though? No, I'm looking for the number who are not. And so what do I have to do? 1 minus in order to get 4 out of 11. Or you could add up the 1 and then the 3 out of 11. That would also work, absolutely. You feel good about where the 11 came from? Why I restricted it down to 11? I think that is probably the trickiest bit here. It's understanding, finding the given probabilities. Okay, let's take a stab at number 4 and then 5, and then I've got one other thing that I want to look at, but we'll call it from there. So number 4, probability of either liking mushrooms or hamburger, given the fact that the person being chosen is not a junior. So how am I going to construct this? And or, so this should be union, given that we are not a junior. Number four, looking at number four. Okay. If we are not juniors, how many people are we potentially looking at? If we are assuming that this individual is not a junior, we are looking at 42. 42. Okay. We have an or statement here. So of those 42 people, how many of them like hamburger? 12 of those 42 like hamburger. And of those 42 people, how many of them like mushrooms? 7. Who are not juniors? Who are not juniors, so 7. Yeah. And is there any overlap? So did we have, at least as far as this is indicated, anyone who said that their favorite is both mushrooms and hamburgers? No, if there's no overlap, then these events must be mutually exclusive, and therefore we get that this should just be 19 out of 42. Okay. Probability of liking onions and being a sophomore. How would I write this? O and S. All right, notice here it's not conditional. We're not making any assumptions that we know what's going on. We certainly could drum up some kind of conditional probabilities. That would be fine. If I wanted to compute this kind of mathematically, what is my probability of getting onions? 17 out of 60. What's my probability of seeing a sophomore given that they like onions? 9 out of the 17. And so I get 9 out of 60 total for that probability, which also, go figure, is that 9 that we see right there. Cool. And that's it. That's 4-3. Which is, again, really just what we have been doing up until this point, but, or 4-4 rather. Well, it's, both. Done with both now. But yes, that's 4-4. Any questions with our set notation stuff? Nine out of, so there were 17 people who we said liked onions. 9 of those 17 were sophomores. Either way, it's fine. Same deal of like with the partial credit of like if you just give me an answer, then I can't give partial credit. But like if it's like a just super obvious thing, and the work, you don't need to do like the whole like the notation necessarily of like the p and whatever. But if you just like show me the things that you're multiplying, then that can be helpful. Yeah, go for it. Yeah, grab all pass. Okay, one final thing that I want to cover today. This is a clarification on terminology that I have been, I'm not willing to say I've been using it wrong, but I've been a little bit more restrictive in how I have been using it up until this point. The good news for us is that the math has not changed whatsoever. What I want to consider, though, is what I was originally calling the difference between a simple event and a compound event, which we are going to see is, in fact, these are both compound events. So I want to take a look at within one role. The probability of getting an odd number and getting a 3. And I want to look at with 2 dice rolls, the probability of getting an odd number and a 3. So you'll notice here the notation between these two is exactly the same, even though the events themselves are very distinct, very different. Which is why part of my motivation for wanting to talk about this is that the notation here is kind of bad in that you can use this to communicate both of these ideas and you get very different probabilities. Okay, so first of all, my definition of an event up until this point was the actual action that we are performing, right? So whether it's tossing a die or flipping a coin or what have you, that was an event. And then the A's and B's that we were looking at were like the conditions that we might satisfy for a particular event. That is not correct. The A's and the B's are the events. So for instance, in this case, I have 2 different events. I have 2 different conditions. The first event is getting an odd, and the second event is being a 3. Since I have 2 different events, this is a compound event. Even though we are only rolling a single die, this is compound because there are multiple kind of conditions that are being filled. Okay. So everything that I was saying before as being compound is still compound. So if it's 2 dice throws or 2 coin tosses or what have you, those are requisitely compound events. Each condition stems from a different action, but we could also have a compound event where each condition stems from just a single action, right? Thinking about the outcome being like an individual taking a test versus being positive, the individual is the outcome, and then it's just 2 different conditions, the score that they got on a test versus the result that they actually have in real life. Okay. The good news for us is that the computation between these two is consistent. Right. So regardless of how we are dealing with this, it doesn't matter if it's for multiple polls or multiple rolls or what have you, or just one. You'll notice here, I say that the multiplication probabilities are for multiple draws. That is true, but it is not exclusively the case. We can see that here that we can apply the exact same principles. So based on my multiplication rule, what is the probability of getting an odd and a 3? How could I write this in terms of my multiplication? Some good notes that we just took that might be helpful in answering this question. What's our multiplication rule with probabilities, with and statements? Yeah, it's the one that incorporates the given. So what is this? So we're going to look at just the one rule first, and then we're going to look at the 2 rules. So yeah, you can kind of think of there being a conditional on both of these. This is like given that one rule takes place, given that 2, but we don't really need to quibble about that too much. We're not going to try and integrate that into our formula here. It's just what is the formula for P of A intersect B? Yep, you got it. B given A. Perfect. So what should the probability of rolling an odd and a 3 look like? Well, just like formula-wise. Well, we'll talk about like what would we expect the odds to be here? How many outcomes satisfy both of these conditions? Just one, right? Should just be a 1 in 6 chance, right? If they get a 3, that's the only one that satisfies both of those conditions. So we know that it should be 1 in 6. Let's show that through our calculation here. What is the formula going to look like for the probability of getting an odd and a 3? Not really. Funny enough, you get very different looking results, but no, ultimately it doesn't matter. Not a trick. Yeah. 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 Very good. So this is the probability of getting an odd times the probability of getting a 3, given that the result that we saw was an odd. So first of all, what is the probability of getting an odd? 3 out of 6. Okay. Now, assuming that we know that our result is odd, right? Given that our result is odd, how many numbers do we have to choose from for our standard D6 if we know that the result is odd? There are 3 numbers that are going to give us that. And then of those 3, how many of those are going to give us a 3? Only one of those 3 gives us a 3 for a probability of 1 in 6. Liz asked a great question here, which is what if we reversed it? Which we should be able to do, right? The probability of getting a 3 and an odd should be the same as the probability of getting an odd and a 3. What's the probability of getting a 3? 1/6. What's the probability of getting an odd given the fact that we have gotten a 3? 100%. So 1/6 times 1 gives us 1 in 6. Absolutely correct that we can do this in any order, and it should work out to be the same. Now, of key note here, are these events independent or dependent? These are dependent, right? Notice that the probability, as soon as we knew that what we saw was odd, the likelihood of it being a 3 goes up. The likelihood of it being a 2 would plummet down to 0, right? But the likelihood of it being a 3 doubles. And so these are dependent events, right? This is a complex, or not complex, compound event in particular, but with a single die roll, which again was contrary to what I was saying before, but this is how we deal with it, right? A single die roll is going to lead to these 2 kind of dependent events. Okay, with our 2 die rolls, again, what is our probability here? Well, it should be the same, right? It should still be the probability that we get an odd. But now the interpretation is a little bit different, right? This is saying the probability that the first roll is odd times the probability that the second roll is a 3, given that the first roll is not. Okay, what is the likelihood that the first roll that we see is odd? Still 3 out of 6, still the exact same. Now, given that the first roll was an odd, would we expect that to have any kind of bearing on the second roll? No. We wouldn't expect the first roll to affect the second roll at all. Therefore, these are independent events rather than dependent events like we saw originally. And so what is the odd of us getting a 3? It should just be 1 in 6. Right? Unaffected by what we got before, this should just be a 1 in 6 chance. And so this is a 1 in 12 chance when we are rolling 2 die versus a 1 in 6 chance when we are not. right. But just wanted to clarify this point. All right, questions here with our kind of compound versus simple. And I know I messed it up a little bit. My bad on that, but similar idea. Or really at this stage, anything from particularly 4.3, which you guys have a quiz on tomorrow, that we would like to go over during this time, since we have about 25 minutes for you guys to work on your classworks. Anything from those classworks that will be on the quiz tomorrow that you would like to discuss.
So do we get to use our notes for objectives?
No? Yeah. You're good. Do you want to grab a hall pass to go? All right. Well, if you guys have questions as they turn up, more than happy to take a look at any of those. But beyond that, you guys have the rest of this time to work on your classworks. Again, just ask away if you have anything that you would like to go over.